Let's move to analyze the criteria that we can follow to recognize a fractured reservoir. To recognize a fractured reservoir is the last presentation of the first group of presentations focused on a general review of the fractured reservoirs. In fact, to address the question, is my reservoir a naturally fractured reservoir, is not always straightforward, and in some cases this question can remain unresolved for many years after field discovery. As already mentioned in a former presentation, the statement all reservoirs contain fractures but not all are fractured reservoirs is a good introduction to the question, what is a fractured reservoir? Question that is addressed by the definition, a reservoir in which fractures enhance the permeability at field scale, thereby significantly impacting well's productivity and recovery efficiency. So rocks affected by stresses during their geological history are fractured, and when the role of these discontinuities impact significantly on the flow capacity and storage capacity at field scale, we have to deal with the fractured reservoir, that are the type 1, 2 and 3 as per Nelson classifications, illustrated in a former presentation. So the presence of fractures is a condition necessary but not sufficient to define a reservoir as fractured. In fact, to have a fractured reservoir, the presence of fracture must be significant to impact the rock matrix permeability. The recognition of a fractured reservoir is not always straightforward, because the understanding of the role of the fractures and their interplay with the rock matrix can be tricky. To have a fractured reservoir, we need an effective continuous fracture network that reaches the percolation at field scale and overshadows the role of the rock matrix. In fact, 4 features impact on the connectivity of the effective fracture networks: intensity, orientation, length, and aperture. In the plot on the left, describing the fracture intensity on the x-axis versus the effective permeability on the y-axis, different fracture networks are sketched. We can see that for a given fracture intensity, the fracture network permeability can be quite different in relation to fracture orientation and length, impacting on the percolation threshold. Of course, also the fracture's apertures are bound to affect the permeability of the network. The diagenetic overprint and the currently acting geostress can have an impact. The diagenetic overprint can increase by dissolution and corrosion the original aperture, as well as reduce them by cementation. In fact, fractures can be sometimes even totally cemented, and so they can represent, in this case, a kind of permeability buffer. On the other hand, the present tectonic stress can increase or reduce the fracture's aperture in relation to the orientation of the fracture planes with respect to the orientation of the maximum stress. Fractures oriented perpendicularly to the maximum stress are bound to be more closed than fractures parallel to the maximum stress. So the orientation of the geostresses currently acting on the fractures can influence their aperture and permeability. Therefore, the presence of fractures in a reservoir is just a part of the story, and we cannot give for granted that we are dealing with a fractured reservoir. In fact, to recognize a naturally fractured reservoir, we have to rely not just on the direct observation of fractures, but also on the indirect observation as inferable from the dynamic behaviors that mirror the actual impact of the fractures at a larger scale, at a reservoir scale. So, What are the evidences or the clues that highlight the presence of a naturally fractured reservoirs? Actually, there are a lot of evidences that we are going later to list, but let's start with the heterogeneity in productivity. That is probably the main evidence that highlight the presence of a naturally fractured reservoir. That means few wells with high productivity versus large number of wells affected by lower productivity, as highlighted by the productivity index frequency plot on the right. This behavior is a consequence of several factors affecting fracture network. Fracture network spatial discontinuity, fracture intensity variability, fracture characteristics variability like orientation aperture, fracture permeability much higher than rock matrix permeability. These characteristics are bound to impact on the rock permeability in a very abrupt way. Actually, any geological context is affected by multiscale heterogeneity impacting on permeability, like for example, heterogeneity at a small scale in relation to the role of the selective transport, heterogeneity at a larger scale in relation to the sedimentological bodies, vertical heterogeneity in relation to grading and layering, and of course, heterogeneity in relation to the presence of microfractures and fractures that can cover a wide spectrum of scales. We can observe this heterogeneity from different scales of observation, from the core plugs, from the full-size core, from the single well logs and with the wells correlation, from the well test. However, in particular, the impact of the fractures heterogeneity at a larger scale is very difficult to infer because of their discontinuous distribution that is very difficult to predict. So for a very homogeneous rock like a sandstone, the permeability estimated from small samples like the population of core plugs is bound to have a scattering of permeability values that is quite confined and very similar to that of larger samples, like the population of core full size. And the relevant representative elementary volume is very small and easy to infer, and the heterogeneity is not a problem. For a heterogeneous not fractured rock, small change in location means large change in property, and the relevant representative elementary volume is larger, more difficult to be estimated. This situation is exacerbated in naturally fractured reservoirs, where we have the presence of two media, fractures and rock matrix, characterized by permeability which differ per order of magnitude, and fracture distribution is very scattered and uncertain. Plugs and full-size core include generally only a part of the fracture network, and the representative elementary volume exceed their volume. Therefore, the fractured rocks are affected by a large-scale heterogeneity, and the relevant representative elementary volume should include the representative fracture network that is generally much larger than core samples. Moreover, it is bound to change by areas in relation to the change of fracture network characteristics. The presence of fractures is mirrored in the heterogeneous dynamic behavior at field scale, as illustrated by the well dissimilarity plot here reported, where on the x-axis we have the normalized number of producing wells ranked for decreasing cumulative production, plotted versus y-axis the relevant normalized cumulative productions. Looking at the different fractured reservoirs, we can see that type 4 reservoirs, as per Nelson classification, are characterized by a quite homogeneous behavior being controlled by the characteristics of the rock matrix about equal all over the field. This means that the 30% of the wells, for example, will contribute to the 30% of the cumulative production, because all the wells have the same performances. Moving north-eastward in the Nelson plot, we face an increasing heterogeneity highlighted by fields where few wells perform better than the mass of the other wells. So, for example, in these type 3 fields, the 30% of the wells, the best ones, contribute for the 55% of the cumulative production. Moving to type 1 reservoir, top right corner in the Nelson plot, we have that the 30% of the wells, the best ones because crossing fractures, contribute for a large part of the cumulative production, about the 80% with respect to the large number of wells with quite poor performances because draining just the rock matrix. So we can say that in this kind of reservoir, crossing fracture makes the difference. We can make a list of the indirect observation that could suggest the presence of a fractured reservoirs. Apart the productivity heterogeneity already discussed, we can mention high well test permeability thickness, high absolute open flow, high productivity index, high flow capacity index, that is the ratio between the KH well test and the KH matrix as inferred from core data, dual porosity behavior as observed on well test, productivity improvement factor that is related to the better performance of the horizontal wells versus the vertical wells because of the higher probability of crossing the vertical fractures. Isolate interval of high productivity in poor reservoir rock. Significant gas show in low permeability rock. Rapid productivity decline. Rapid rise in gas oil or water oil ratio. Well-to-well high hydraulic communication. For example, productivity index is more heterogeneous in fractured reservoir, and the different values have generally a scattered spatial distribution. So, looking at the two underlying bubble maps, where the size of the bubble is proportional to the productivity index, the more scattered scenarios reported by the map on the left would suggest the presence of a fractured reservoir. However, we must be cautious because a fault zone with relevant fault-related fractures could lead to a less spatial scattered scenarios. Another very important indirect fractures indicator is the flow capacity index, that is the ratio between the KH well test and the relevant KH matrix as estimated for the rock matrix on the basis of the core data. Ratios largely exceeding 1 suggest the presence of enhanced permeability not captured at the core scale of observation, and so the possible presence of effective fractures.